Thank you for the introduction, and thanks for having us, and thanks for showing up. Also, it's almost lunchtime. We are talking today about Christian and myself, about what we're doing at Audi with big data, especially in the fields of production and logistics, and we brought a project with us from the Automotive paint shop. To give you more of a background why we are doing that, why is an automotive OEM dealing with things like big data, we have a very clear strategy at Audi. We call it the Smart Factory, and this is how we want to achieve the future of our intelligent production. And one of our focus areas is the so-called digital production, and that's where like the fields of big data, analytics, machine learning, deep learning, AI are located. And the question is always with strategies, how do we achieve that? Therefore, we decided to aim for a vision, and that's the data twin or the memory of our production processes. We want to save all the data, analyze all the data we have. And on this way, we have 4 missions we want to achieve. Like one is the infrastructure topic, like there are things like next level Wi-Fi, 5G, and things like that, not topic of today. The next one is connectivity, how to enable machine-to-machine communication, things like MQTT standardization, OPC UA, things like that. Also not topic of today. The third one, that's the topic of today, is how do you store all this data with increasing connectivity of robots, machines, and stuff like that. How and where to store this data. And last but not least, what to do with the data you store there. And to achieve things like that, we founded a few so-called tech hubs. We have one tech hub for our digital production. We also have a tech hub here in San Francisco dealing mainly with car data. And those are the main innovation drivers where we try to solve the problems of our own future. As I assume most of you are not that familiar with production processes of an automotive OEM, I will take you on a short tour. When we produce a car, we start with huge metal coils, which are put into huge molding presses, which produce the essential parts of a car, like side frames, lower parts, roofs, doors, whatever. After that, the pieces are being put together in a body shop, mostly by robots, using different technologies, welding, gluing, riveting, screwing, whatever is best in that case. The next one is, and that we will cover that in more detail in a few seconds, is the paint shop. That's quite easy. That's where all the color goes onto the car. And the final step actually is the so-called assembly shop. That's where the massive puzzle is being put together. As you might imagine, with premium automotives, we make mostly build to order. And that means we don't produce 2 same cars. And that's a highly complex process, especially in the assembly shop. And additionally to that, we have some supporting processes like logistics, like manufacturing of engines and components like gearboxes, and all this has to fit together. The project we are bringing with us today is out of the paint shop. It may sound funny, but painting a car is not a simple process. It depends on a lot of different influencing factors. Some of them you already know, some of them you don't know, some of them you can influence, others you can't influence. And that's a major topic. Not only a lot of things influence the quality, but also there are a lot of possible things that might go wrong when you paint a car. We have a catalog of dozens of possible failures that can occur to a car during the painting. That might be inclusions of dirt, orange peel, shades, and things like that. And all of those have a different root cause, actually. So the main idea was to take all the process data we collect today in an automotive paint shop and correlate that with the defect, the quality data we collect during the production of our cars. In order to make, in the very end, a machine learning algorithm for each paint layer, each possible defect, and allow, therefore, for a faster identification of possible problems and to solve them faster in our paint shop. Unfortunately, we are not in a paint shop, so I have to take you through the paint shop again on slides. But that should give you a short impression about how this works. So once our car comes out of the body shop, it's bare metal, and it's quite dirty. So the first thing we do, we prepare the car for future or for the next steps. What we show you underneath the process step is a few data points. They are by no means exhaustive, but they should give you an impression what kind of data we collect. So if you have any questions later, we can also discuss that. So after we prepared our car, for me the most interesting thing is the cathodic dip painting, which prevents the car later from oxidation. So we don't want our cars to rust. Once that is done, it goes into a dryer. After that, we start with the first layer of real paint, so-called filler, which gives a smooth surface. After that, we dry the car again, bake the color in. Then we go to the base coat, which is the actual color you will see on your car. For a nice and shiny finish, we will give a clear coat. We will dry the car again, and it goes to the assembly shop after final quality inspection. The very good thing at Audi is we don't only do a final quality inspection before we head over to the assembly shop, but after each of those process steps, we do a quality inspection of the car and document them. So we can actually relate quite well which process data led to which kind of defects on the car. In total, around 2,500 variables per car are collected in a modern automotive paint shop. And it depends a bit how often those data are collected. Some of them are collected in the sub-second frequency, and some of them are only collected once per car. So it's quite a vast diversity of data. And now the question arises what to do with this kind of data. Now it is somewhere hidden in the robots and in the plant itself, what to do with it. And that's where our concept of our data lake for production kicks in. You have to read the high-level architecture from left to right. On the left-hand side, we have our sources with different network zones, and on the very right, we have our data lake infrastructure. And we're facing quite a few of challenges of that. First one is we are facing different network zones. We have an international production network on multiple continents, and each production site is actually protected within our own network zone, mainly due to the security reasons. That also means each of the data sources located in those plants is completely isolated in the first place. The second one, we have very heterogeneous data sources from files on file systems like pictures of defects and things like that, ranging over databases. We pretty much have all of them, from MySQL, Oracle, IBM DB2, MongoDB, whatever you can imagine, we probably have it somewhere, all the way to robots. So directly logs or protocols coming directly out of robots. And in order to deal with that, we developed a service bus-like architecture called a middleware, or our integration server, which collects data from all the data sources located within one network zone and sends it via a central data proxy where we use Kafka to our data lake infrastructure. And the data lake itself is actually a data platform. It's Hadoop-based, so we're storing the data in HDFS. Tabular data we are making accessible via Hive. And we are sharing this data platform together with our other business departments. So it's not an isolated silo for production, but we rather think about cross-functional use cases together with field quality, what you heard from BMW. We are talking about sales, after-sales data, all this stuff, technical development. So now that all our data is stored in our data lake, our data is ready to be used for further projects, for example, like the root cause analysis, which is what Christian is going to present for you.
Okay, so also a warm welcome from my side. So let me introduce myself shortly. I'm Christian, working at Audi Business Innovation GmbH, which is a 100% subsidiary of Audi, and we are located in Munich in Germany. So I will talk a little bit about more detailed what is the technology stack we used, especially what we did with Spark, how the processing chain looks like, explains some challenges we had during the implementation. And yeah, so let's start with technology stack. So the whole thing is based on Hadoop, and as Christoph already mentioned, we store all the different sources in Hadoop file system. We have Yarn Resource Manager on top, and on top of that, we have the whole Spark ecosystem. So with the Spark core, of course, we're using the data frame API and the Spark machine learning API. So in more detail, what are we storing there in the Hadoop file system in HDFS? So it's mainly 3 data sources we are using to do the analytics. First is the vehicle control points. So this is more or less timestamps, which vehicle enters what stage within the paint job. Then we have process values. This is all the measures, all the sensor data we are collecting in the paint job. Obvious one like temperatures, like humidity, more paint job process dependent ones like painting pressures and so on. And finally, we have failure data. So failure data is which problems occurred during the paint job process. So this is partially just mainly entered by some specialists who can just see these partially very small quality problems. Partially, they are collected automatically. We decided to store all this information in Afro format. I will come later on why we decided for Afro. Okay, on the Spark ecosystem, we started our implementation with 1.6. When we started with the project, we migrated to 2.0 during the project, which was not a trivial task. When we did the first compile on the code, we got thousands of errors, so was work of some days, to do the move because the code base was already quite large. We decided when we start with 1.6 to use the data frame API. It was already mature enough. We got much better performance than just using RDDs. And we wanted to use the data frame-based machine learning library. So as programming language, we implemented everything in Scala. Main reason for Scala was also performance issues. I think it's much more robust by means of developing software than using Python, for example. And you can leverage on skills you have already. So because our team has a strong software development background, so Scala is a natural choice. Another important reason, I guess, and you heard this already in other talks, when you start debugging your code, you can really go into the Spark code itself, and if you do all the stuff in Scala yourself, you have a really much better understanding what is going on under the hood. So if you come from Python and you have then to go into the Spark Scala code, it's quite hard. And there are a lot of, let's say, there's several problems that occur during development where it really helps when you go into the Spark code to understand where the problems come from. So on the machine learning part, we mainly do classification, and we use the random forest with its cross-validation capabilities more or less out of the box, what brings Spark on there. Okay, so let's move on with an overview of the workflow. So we have mainly 2 processing chains. So one is daily processing, another is a weekly processing chain. And the daily processing chain is more or less the data ingestions and transformation. So we start transferring the data from the paint shop. This project was especially implemented for our paint shop in Győr in Hungary. So the data is transferred via our data proxy, the Kafka-based data proxy, to our Hadoop cluster in Ingolstadt in Germany. Mainly, it's the three data sources I mentioned already, so the vehicle control points, the process values, and the failure data. We store the data there using Afro. So we decided for Afro because of its embedded schema capability. It's row-based, so for our use case, we more or less read always most of the rows, most of the fields. So row-based format is, for that use case, in favor of a column-based use case like Parquet, for example. And we have Spark and Hive support built in with Afro. Next step is data cleansing. Nothing special here. Filtering, of course, syncing data sources, the types, naming conventions. What we have to care a lot about is date time handling, and we have different time zones in Hungary and in Germany, and even the systems in Hungary run different time zones. So because at the end, the most of the transformation is based on matching the different data by timestamps or period of times, you have really to care about that the handling of dates and times is correct there. Okay, then we come to the data transformation. So in this phase, the biggest part is joining the different data sources, especially vehicle control points with the process values via timestamps, and this was also one of the biggest challenge. I will come in detail later on. And the second is we have to aggregate all the stuff to our analytical base table, where we have then the entity we look on, not just the vehicle. It's in detail, it's a vehicle and the run, because a vehicle can go through the whole paint shop, or at least through parts of it more than once. Okay, we persist the results that we do in this daily processing and store it again in HDFS. So coming to the weekly processing chain, this is where we do more or less the modeling. So we prepare the analytical base table, and what we do here is we aggregate the data that we process daily in the daily processing chain, and put together always 4 weeks, and we do it in a rolling manner. So this process is run once per week, always for the last 4 weeks. We create the target variables for each paint layer, and we create the predictor variables. We have more than thousands per model, normally up to 3,000, I guess, at the moment, to do the final modeling. As already mentioned, the modeling is random forest classification. We do know, we are not really, currently not mainly interested in doing predictions, but we are interested which variables are the most important ones that cause our failures. So we decided, or this was one of the reasons that we decided for random forest, because random forest has the variable importance capability already included in the implementation that comes with Spark. Okay, and finally, of course, we are storing the results. So this is mainly the variable importance itself, model quality measures, and all these results are accessible via Hive tables for further mainly visualizations. Okay, so as already mentioned, one of the main challenge in this project was joining the timestamp-based data. So on one side, we have all the process values like temperatures, humidity, more than thousands for each model, which have different periodicity, We have sensor data that come in per second. We have sensor data come in per minute, some just every 2 or 4 hours. And on the other side, we have the vehicle control points. So remember, vehicle control points are more or less the timestamps when the vehicle enters a certain stage in the whole process. So what we want to do is that we want to join the sensor data to the right control points. So joining means we have a huge amount of process value data, and also the amount of vehicle control points is not really small. So joining on them with that join condition that the timestamp must be in the period is not trivial. So what was the solution for that? We partitioned the whole data in period chunks and gave IDs for that and joined just on that IDs. We do the daily processing. So and finally, we do heavily based on broadcast variables or broadcast joins. This helps really to improve the performance when you do this when you use this Spark feature. So another problem or challenge that is dependent on that joining problem is how to aggregate the data. So for example, you could have one sensor data with that distribution, and you have 3 data points within that interval. So for example, you could just do an average. Another sensor data maybe has that distribution. You have no data point within that interval. One approach could be doing just interpolation or last occurrence carry forward. So this is mainly dependent from the variable itself. So we decided to solve this problem that we implement several aggregation methods, and we can configure per variable which from these aggregation methods applies to which variable. To show also some code, as already mentioned, we use Scala. Everything is implemented in Scala. As you can see on the left side, this is just a small example of these different aggregation computations in a more or less object-oriented style. Probably it developed from somebody who comes more from the Java world. On the right side, you see one of the core parts where the joining is done itself. So for us, using Scala is really the nice thing is you can leverage from both the object-oriented, from the functional paradigm. You can leverage also on all the development infrastructure tools like continuous integration, continuous deployment, and this helps you really if you build up, let's say, a larger use case where it's, I think, not possible to have just some notebooks with some pieces of code where you have a really more complex software solution. Okay, so the second challenge I want to have a look on is that we have unbalanced target variables, of course. So fortunately, most of the failure types are very rare, so like under 1%. So you have to do something to get quite well-performing models on that. So what we decided for is that we do random oversampling instead of undersampling. So this increases the accuracy on the training data, of course, with cost of overfitting, but as we're just looking on the variable importance and don't want, at least now, to do the prediction itself, this fits quite well for our use case. Another thing that solved that improved the problem was increasing just the time periods for modeling. So we started with a daily modeling, a weekly modeling, and so finally we came to the 4 weeks models that performed quite well. And of course, you have to pick the right performance metrics to evaluate the models like F-measure or the ROC curve. Okay, so conclusion will be done by colleague again.
So, yeah, thank you. So once you've done all this stuff, the main question is always what to do with it. And therefore, we developed something we call the paint shop cockpit, which we are ready to roll out also in other paint shops in Audi. And it has different visualizations ranging from like very classical reporting with interactive methods, where are my main focus areas, where I have to look at to the point of what are my results of my machine learning results, my root cause analysis. And this can be used today by different business departments in order to find the reasons we might have problems with our quality during our paint shop or during our painting process. And to give you an idea of what those results are, we found it's not about the trivial ones. Yeah? Everyone who has a bit of knowledge about painting a car knows it shouldn't be too hot, it shouldn't be too cold, it shouldn't be the humidity shouldn't be too high or too low. But it was about the very interesting facts. Like, for example, you have fresh air ventilators for the paint cabins, and it definitely matters how much fresh air you need. Fresh air for cars or for painting cars is not always good. And that's something, once you know that, you can also change your process, steer your process differently, and therefore make an adjustment that in the very end results in better quality. Another interesting thing, I liked it a lot, is we use a special sand, so-called rock meal, which is used to cover paint overspray. So not all the paint goes directly on the car, but rather some of them is lost in the cabin, and therefore you use this special sand, which is supposed to capture that. And then small vibrations or detonations are supposed to clean paint clumps. And normally you don't do that when the car is in the paint in the paint cabin. But we found out with our algorithm that it's not only that the car has to be in the cabin, but it shouldn't also be near the cabin. So things like that, cleaning maintenance purposes, have to be steered differently in order to achieve the most accurate or the highest quality possible. So those are only two of the findings we got out of our first phase, and things are continuing. So all I have to say is thank you for being here, and if there are any questions, you're welcome.
Okay, question about two things. One, what if you find a car, you guys going back and looking at data from a car later on, 2 months later that has come back and has a paint issue, you going back to capture that and look it up in there? And the second thing, is there any kind of alerting that goes on that the fresh air is at the wrong temp or wrong levels right now?
I'm not sure whether everyone understood that. Two things. The first thing is once probably a customer comes back to us and says, hey, I have a problem with my car. Actually, yes, we can do that now with our data lake infrastructure sharing across different business departments. If someone comes back to the workshop, you can actually look it up and say, okay, what went wrong with the car? But we are quite confident that we don't have any such problems. That's the one thing. And the second thing is definitely something from my perspective for next phases. With this project, we had to build a lot of trust with our business departments. So production guys are not always, they don't like that fancy stuff of analytics, machine learning. That's quite, they are not dedicated to that. So that was the first phase where we said, okay, we want to see whether we get meaningful results out of it. And the second or third phase definitely has to be, can you directly feed that back into the process? In the very end, actually, can you build something like an autonomous production? Like something goes wrong, you detect it, and you feed it back in the machine. Don't use that much fresh air and directly regulate your process. Yes, that's the goal, but that's not where, at least, we are right now. But we're working on that.
Are you ever having to change anything based on new robot? It's feeding new data, or you got a new vendor for paint, any of that kind of stuff goes in your model, I'm assuming.
Yeah.
Great. Thank you.
You're welcome.
Any other questions? Okay, thank you. I think it's lunchtime.